All right, in this video, what we're going to do is the definition of derivative. It's going to be the first case where we actually use the limits to define the thing that we want. The two main things that we want in the calculus of variation, one is the definition of derivative or instantaneous rate of change of the function, and then the reverse of that, antiderivative, or how we're going to compute limits at infinity eventually at the end. Right now, what we're going to do is we're going to compute a limit at a finite value and get that to be a finite limit. And that's why we wanted these limits in the first place, was to define the derivative. And then later at the end of the course, we'll also use limits at infinity, which we just talked about in 4.3. We'll use those to define the Riemann sums or definite integral, which is related to the antiderivative going the other direction of this, the reverse. All right, so the picture is we have a function. We want to know what its instantaneous rate of change of that function at that point, and that's what we're going to call the derivative, or f prime of a. What that means is we know what the rate of change of a regular straight line is. A regular straight line says we can find the rate of change if we look at rise over run. Rise over run. That's supposed to say rise. Or it could be riz, I guess. Rise. Got some riz in there. Rise over run means what? We have the change in y over the change in x. If we look at this specifically at this point here, at this secant line, again, secant, secare in Latin is to cut, and tangere is to touch. So we're going to find one line that just touches it, the tangent line to touch, out of these secant lines. How are we doing that? First, we're looking at the rate of change of all of these straight lines is just rise over run, which is the slope. The slope of the secant lines is rise over run, which in this case, when we have these weird points, at that point, this is the point A, f of a, and this is the point a plus h, f of a plus h. So at those two weird points, because they're on the graph of my function, specifically in R2, the slope of the secant line looks like this when I phrase it like this. Also, the a's cancel here, and that's why it's always just an h on the bottom, and you forget that it's the slope of a secant line. Then what we're going to do is we're going to take that delta x, or we're going to put the h as h goes to 0. We're going to look at the limit. A plus h is going to move to a, and we're going to get secant lines that cut it closer and closer until we get a slope of a secant line, which is exactly going to change it or touch it just at one spot. That's going to be the change of the function, we're going to call it. No, I was right. So what do we mean by that? The slope of the tangent line is going to be the limit of the secant line, which is that guy, and that's exactly what we're going to call f prime of a, or the derivative, or the instantaneous rate of change. The slope of the tangent line, that's a lot. That's three things, but they're all the same thing. The slope of the tangent line, the slope, not the whole line. We'll describe that in a second. That's the linear approximation, and differentials is what they're going to talk about with the entire equation. But the slope of that tangent line, of that limiting process of the secant lines, is the instantaneous rate of change of the function. Because we're looking for the rate of change of those lines, they touch exactly at one point, but they touch there, and the value of f equals the value of the tangent line there. So their rate of change will be exactly the rate of change of this straight line, which we can compute as this limit. And that is exactly what we're now going to call the derivative. So the derivative of f, or f prime of a, is how we're going to read this. F prime of a is the derivative of our function at the point a, which is its instantaneous rate of change and the slope of the tangent line. It's the derivative, it's the slope of the tangent line, and the derivative means rate of change of the function, instantaneous, not average rate of change. This is average rate of change in that interval. Let's reorganize that for a second and compute a bunch. So What are we doing again? Let's start one more time from the beginning, and then we'll do this for a couple functions. And then in the next video, we'll do just the major cases of what they're going to try to do to you. So then when you have an exam, you can try and muddle your way through the dirty tricks that we're going to do in these different types of limits that we had and get ourselves out of them. What are we going to do first? We have our function, say, and we want to know what the derivative is there. So then we have a, and we move out a little bit, a plus h. The f average of a function on an interval a plus h is equal to rise over run, which is exactly going to be f of a plus h minus f of a over a plus h minus a, cancel. So the average rate of change on this interval is going to be rise over run, delta y over delta x. And then if we take the limit of that, that is exactly f prime of a is equal to the limit as delta x approaches 0 or h approaches 0, because h is delta. So I wrote the delta again. But as h approaches 0 of f of a plus h minus f of a over h. This is also the slope of the tangent line. And so it's those three things. As we take that limiting process, we have one, it's the slope mt of tangent line. The tangent line we're going to build is y tangent minus y1 equals m tangent, this guy, times x minus x1. That's the equation of the line, which has specific values at a. We'll get into in a second, but that's the equation of any, this is the point slope form of any line. We have specific values for those guys, which we'll get into in a second, and that for the entire equation. But for now, it's the slope of that equation of the tangent line. It's also what we call the derivative of f at x equals a, or f prime of a is what we're writing. And then what is that? It technically is f prime of a, means it's the instantaneous rate of change. Of f at a. And how we're doing that again is, oh, we lost him. How we're doing that again is we're moving h to 0, and we'll get one equation of the tangent line, and then we have that the rate of change of the nonlinear function is exactly equal to the rate of change of the linear function, which we know is slopes rise over run. That's the clever idea. Derivatives. Thank you, Sir Isaac Newton. Let's do an example. Before we start, I'll write it down, but it's going to be each one, and I'll write it down as a mantra. Example, what's the mantra for doing this? Mantra for derivatives by definition. What's the mantra? Do you know? No. That's why you're here at the wizard's house, the wizard hut. Okay, so what we have is h is going to 0 always. That's why I look there every time. There's always a problem. We're always doing over h, f of a plus h minus f of a. So we always have h as a problem. Yes, problem. So how do we get it to not be a problem? If there's any justice in the world and we have something, h has to come out of here. So get h out of numerator. That's what we're actually doing, numerator. That's what we're actually doing. And so whichever game we're going to use, how are we going to do that? Algebra. The algebra that we've done, conjugate and factor and all these things, and FOIL, etc., common denominator. Those are going to be the three major ones. We have to use algebra to get h out of the top so we can cancel it with this one, so then we can push h to 0 and get our number. The real game here is get h out of the top. That's the mantra, to cancel it with the bottom. In each one that we do, this is what's happening. I'll do one of each, and then we'll combine them at the start of the next video. So that's the mantra that's in my head. Classically, the three algebra techniques that they have is expanding everything. That's why we use the h definition. I'll remind you of this in the next video. So expand everything, or FOIL, And then the other one we have is if we have a fraction, which we're always going to have, get a common denominator. Or what we might have also is a square root. And how do we get a square root over something? We conjugate to get rid of the square root, which we did in the last video with the limits at infinity. We conjugate to get rid of the square root. Let's do it. Move it. It moves it. So example, the first one I should do is a polynomial. That's going to be f of x is x squared plus 1. And we're just going to do compute f prime of a for this function by definition. No marks will be given. It doesn't matter. It's a video practice. So what are we going to do? I see that this is a polynomial, so we're going to use FOIL, or first, outside, inside, last, or expand is really what we're doing. Why? Because I have to do f of a is going to be a squared plus 1. F of a plus h. I dropped it. Oh, got it again. F of a plus h is going to be, here's where I have to use it, a plus h squared plus 1. I have to FOIL or expand that. That's technically a plus h, if you don't remember, times a plus h plus 1. I expand that. That's a squared plus 2ah plus h squared plus 1. That's f of a plus h. Now what I'm going to do is I'm going to put it in the pot. Do you chop your, when you make soup, what I'm doing first is chopping up the carrots, chopping up the celery, and etc. Now that it's all prepped, now I'm going to put it in the pot and stir. The definition of derivative now is f prime of a is equal to, as a mantra, I probably didn't list it specifically up there, but this is what it is. The derivative f prime of a is equal to the limit as h approaches 0 of f of a plus h minus f of a over h. I've already prepped and found these guys, so now I can put them in there. This is the limit as h approaches 0. This one was a squared plus 2ah plus h squared plus 1 minus a squared plus 1 all over h. So how do I get an h out if it's a polynomial? You factor everything, expand everything, and then everything that doesn't have an h cancels. Remember, there's negative distributes onto both. So a squared minus a squared, 1 minus 1. This gives us now the limit as h approaches 0. Once I expand everything, h will be left in all the terms. So now I have 2ah plus h squared in both terms over h. It's still a problem when it's going to go away. This is equal to the limit as h approaches 0 of h times 2a plus h over h. There. The real mantra is get h out of the numerator to cancel it with the denominator. This is now what? This is equal to h goes to 0, so 2a. That's what we should get. And if you know the formulas, the derivative of this is 2x at every point. So when x is a, you get 2a using the clever formula. Let's do one more. What if you have a fraction? So let's do a rational. Degree 1, let's not get crazy. So f of x is just 1 over x plus 1. I should use a minus, but it's okay for now. Now what do I do? Well, we're going to have common denominator. Once I get a common denominator, I'll get terms in the top, things will cancel, and I can get an h out. The real mantra is get an h out of the numerator. What's the dirty trick that I'm going to use? I'm going to use common denominators, because in this case, f prime of a, straight into it, example 2, is going to be the limit as a mantra as h approaches 0. The derivative is this, which is f of a plus h minus f of a over h, which I'm going to write as the limit as h approaches 0 of 1 over h times. If you know what you're doing, then you can prep it. I'm going to pre-prep it and just throw it in as I'm doing it. I'm cutting the carrots as I'm throwing them in the pot. So what is this one? This is f of a plus h, which will be a plus h plus 1 is f of a plus h, minus f of a will be a plus 1. I know I have, so I'm going to do this. Also, can you see why I'm doing this? I'm leaving room because I know I have fractions, and so I should get a common denominator. To get that common denominator, I should be using, this one's missing a plus 1 over a plus 1. This one's missing a plus h plus 1 over a plus h plus 1. Yes, in this case, it's a 1, so it's going to be fairly nice. Now what's going to happen? Look, once we do the clever move, I knew that because it was a fractional function, I'm going to need a common denominator to get the h out of the top. It should be in the top now, which it is. The limit as h approaches 0 of, now what do I have? A plus 1 minus a plus h plus 1. There he is. Over a plus h plus 1 times a plus 1. Now this is going to cancel, 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 and I'm left with the limit as h approaches 0 of negative h over, I forgot the h over here, the 1 over h times a plus h plus 1, a plus 1. The h cancels now. I get equals the limit as h approaches 0 of negative 1 over a plus h plus 1 times a plus 1. This h now goes to 0. And so once the h is gone and I've got rid of the problem, I can just compute, and this is going to be equal to negative 1 over a plus 1 squared. There's the derivative by definition. What's the algebra? Common denominator. Why did I do that? To get an h out of the top, to cancel it with this guy. That's how you're doing derivatives. We'll do a couple more next time. See you then.